Okay, please go ahead. We are very happy to have Francisco in. He's got his title up here, and we'll let him take it away.
Okay, thank you very much. So I will talk about this new project with joint work with Michael Linowski. We'll talk about, so the title is Manifold Thermology, Eigenform Multiplicities, and the Seifert Weber dodecahedral space. So let me just tell you, I'm currently talking from the Seifert Weber dodecahedral space. That's one of the nice things about Zoom and this virtual gauge theory seminar. So what is the Seifert Weber dodecahedral space? So it's actually one of the first hyperbolic three manifolds that was discovered. So this dates back to the Seifert and Weber in 32. Okay. So the idea is that you can pick a dodecahedron. Okay, and you look at two opposite faces. So if you look at two opposite faces from above, two opposite faces look like this. Okay, so they're not aligned. So what you can do, like the way you build manifolds, like you can identify opposite faces of this, and if you do 3/10 of a turn. Okay, so for example, so you start with this P here, and you end up with this P here, I think. Okay, and you do it for each pair of opposite faces. What you get is a manifold actually, and so around each edge. So if you around each edge, there are five things come in, five copies of the dodecahedron come in. There are 5 copies. Okay, so you have 5 incident copies, and what happens is that you can realize this manifold hyperbolically because there is a regular dodecahedron in H3 with dihedral angles 2π/5. Okay, so they glue nicely. The matrix glues nicely together to give you a nice example of a hyperbolic 3 manifold. And this was one of the first manifold ever hyperbolic manifold discovered. I think Lobel found some examples like the year before, but these are essentially, it's one that it's somehow simple to describe. Okay, and this turns out to be a rational homology sphere. So this is H1. So I call this space Seifert Weber. Seifert Weber. This is Z/5Z cubed. So it's a rational homology sphere. So B1 = 0. And let me just tell you that the volume is about 11.119. Okay, so if you look at the dodecahedron, how it tessellates, you can see from behind me, it gives you this tessellation. Around each vertex, around each edge, there are 5 dodecahedra coming into it. So this is the kind of space. This turns out to be a kind of, it was one of the first spaces ever discovered, but it turns out to be like somehow complicated, right? So I guess let me just mention, for example, so it's quite complicated. Okay, so let me just mention some so Burton, Rubinstein, and Tillman. So in 2012, showed that it's not Haken, so there's no incompressible surfaces inside. Okay, this was a conjecture of Thurston from the 80s. Okay, so it took some time to prove this conjecture. Okay, so even though it's a very simple space to describe, I guess one should think of it as some kind of complicated space. So, okay, and so I guess the theorem that I want to tell today, of course, now we have a three-manifold, which is a rational homology sphere, and we're in a Floer homology seminar. So the question is like, what is Floer homology, or is it a null space? And in fact, I want to tell you this theorem. That's a theorem. This is so I'll tell you today how to show that this is a null space. Okay, so yeah, so I guess of course there are many ways in which one could try to approach this theorem. So I'll tell you today a way using hyperbolic geometry. So I guess a more general question that Michael and I have been thinking about recently. Okay, so given if you have a hyperbolic three-manifold, okay, hyperbolic three-manifold. Okay, then, well, you can build two invariants, right? You can build Floer theoretic invariants. Okay, so in particular, one can look, for example, at some kind of monopole Floer homology. Okay, and on the other side, of course, you have all the topological invariants that come from hyperbolic geometries. So you can look at volume, length of geodesics, and so on. Okay. Yeah, and both these are both these are topological invariants. The hyperbolic invariants are topological invariants by most rigidity. So of course, then there's a natural question: is like, can you tell one from the other? Like, if you know something about one, can you say something about the other, and vice versa? Yeah. So what Michael and I so in 2 years ago, what we did is like, so we showed how to use volume plus complex length spectrum. Okay, I'll remind you in 1 second what that means. To tell whether some rational homology sphere, hyperbolic, is a null space. Okay, yeah, so I guess let me just remind you what the complex spectrum means. So if you have a closed geodesic in your Y, you have the length, so the complex length of gamma. This will be the standard length of gamma as a geodesic. Plus, well, you can pick a orthonormal frame and do parallel transport around it, and it'll go back to another normal frame. And well, but it will come back in a rotated fashion. So that will be some kind of angle. So that will be a holonomy of gamma. Okay, so this is just an angle. So it's some element in 2 pi, real small 2 pi. Okay, so what I mean here is that we have some code that if you give me, if you tell me a space and tell me the volume and the list of all the complex length of geodesic up to length, a certain length, well, our code can tell you sometimes that this space is a null space. Okay, so it's not an if and only if, but it works sometimes. So I guess in our work, we tested our code. Okay, and I guess the first part, this is an introduction, and in the first part of the talk, I will talk about, I'll just talk about our previous work a little bit before going into the new stuff. Okay, so we tested our code on the first manifolds in the Hodgson-weak senses. Okay, so we look. I guess the main example we looked at are the first 50. So the ones which have volume less than about 2.02 something. Okay, so these are, you should think of as some kind of list of very small manifolds, which anyway have some kind of lower bound on ejectivity radius. So for example, what we did was that we showed that the Weeks manifold is a null space. Okay, this is known to be the smallest hyperbolic manifold. Okay, this is the smallest. Okay, yeah, so I guess what we were looking for is like, so the Huxton-Weeks sensors, I think, so downfield computed exactly which of these manifolds in the Huxton-Weeks sensors are L spaces. So the Huxton-Weeks sensor is like a list of 10,000 manifolds which have volume less than 0.6.5 and injectivity radius bigger than 0.15. And I guess, yeah, there's some, I guess most of them are branch double cover over links in S3. Yeah, so and a lot of them are related via surgery to some kind of simpler manifolds. So using this, one can determine exactly which one are L spaces. Okay, so I guess we've been looking for a long time for an example that Nathan at least didn't know on top of his head how to compute. And Seifert Weber seemed to be one of these. I don't know, maybe he just needs to think harder. But yeah, so let me just say, of course, so our method from the previous work, so does not apply directly to Seifert Weber. Well, I guess in principle it applies directly if you have a lot of computational power, but yeah, so because of computational limitations, let's say. Okay, so what we did is like use some kind of refined version that takes into account multiplicities. So we take into account on symmetry and multiplicities. Okay, yeah. Any question so far? Yeah, let me just maybe remark that. Yeah, so I guess the nice thing about Seifert Weber, at least from our perspective, is that it's a very hyperbolic geometric defined object, so it's very easy to access hyperbolic data. It's kind of slightly harder to understand from a topological viewpoint. So Seifert Weber, I guess I don't know, in fluoromology we like to think of stuff either as branch double covers or as surgeries. So let me just tell you that Seifert Weber is not a double branch cover, like a cyclic double branch cover over S3. Okay, and of course it's not a surgery on a knot in S3. Okay, the simplest topological description that I know of is like you pick it's a 5-fold branch cover of the weighted link. Of the weighted link, and it's the one that sends one meridian to 1 and the other meridian to 2. Okay, so it's not the simplest 5-fold cyclic cover, it's somehow the slightly more complicated one. Okay, so I'm not sure if this description can help compute the proof that Seifert Weber is a null space in a more topological way. Okay, but yeah, in principle, one could use some other description and a more topological tool to prove the same theorem. Yeah. Any question? Yeah. So John has a question.
Yeah, I mean, do you know if Seifert Weber is a filling of some one-cusp manifold whose other fillings maybe we do understand the flow homology of?
Yeah, well, yeah, I don't know. It's possible, yeah, but I don't know how one will find this kind of thing. Yeah.
Yeah, you would be to use surgery triangles then.
Yeah, in principle, one could use this bootstrapping argument using surgery triangles to prove it. Yeah, but yeah, I don't know exactly how in practice if that works in a reasonable time at least.
Francesco, is the way that you show it's not surgery on and not just by the width class of the linking form?
Oh no, it's just the H1 is not cyclic.
Oh, duh. Okay, yeah, sorry.
Yeah, the H1 is yeah, so it's not surgery on a two-component link either, I think, right? So it has to be 3 components at least, I guess.
Got it.
Yeah. Mm-hmm. Yeah, so the fact that it's not a branch double covenant tree will come up this later, and it's because we really understand well the isometry group, and it's a very big group. Yeah, so in particular it has order 5 and order 2 elements. So that will play an important part in our work. Okay, so let me, I guess for the rest of the talk, the first part I will just want to review a little bit how the machinery that Mike and I developed works in the case of, and how it applies in this case of a small manifold. And then the second part, I'll tell you how, well, where the computational barrier comes when you look at Seifert Weber. I guess you can already think that it comes from the fact that Seifert Weber has a very big volume compared to this other manifold that we were looking at. Okay, so it's here. Yeah. So if there are no other questions, I'll go and review our previous work. Yeah. So yeah. So let me. So we'll focus on the case of manifolds with B1 equals 0. Okay, so a rational homology sphere, and it's interesting because there's this dichotomy L space, non-L space. Yeah, so you have the Hodge Laplacian acting on, which is D plus. So here we have a Riemannian manifold, like with a hyperbolic metric, let's say. So you can look at a Hodge star with respect to the Riemannian, to the hyperbolic metric, and this acts on 1 forms. Okay. And the Hodge theorem tells me that it splits as the direct sum, orthogonal direct sum of exact forms, so stuff which is d of a function, and d star of omega 2. So this is coexact. Okay, so yeah, and the Hodge decomposition, the action of the Laplacian preserves these 2 components. And I look at the spectrum of the Laplacian on the second part. So I will have 0 less than lambda 1 star, less or equal than lambda 2 star, less or equal than lambda 3 star, and so on. Okay, this is the spectrum on d star omega 2. Okay, so these are the coexact eigenvalues. Okay. Yeah, so this first quantity turns out to be important when thinking about L spaces. So this is the theorem. So this is from our previous work. So if B1 y equals 0, and you have a hyperbolic rational homology sphere, okay, if lambda 1 star is bigger than 2, then Y is an L space. Okay, so you can think of this is some kind of a souped up version of the standard fact that if you have a metric with positive scalar curvature, then your space is an L space. So this is somehow taking into account a little more the underlying geometry of the manifold. So and in particular, this is again like some application of Bochner techniques allows you to prove this kind of thing. So in particular, what you show is that if this is true, then there are no irreducible solutions for the Seiberg-Witten equation for small perturbation. So it's even stronger than being an L space in the standard sense. Okay, yeah, so I guess let me just remark the way I like to think about results. So you can think of the contrapositive. So this is somehow saying, this says somehow that, well, you can think of it, the contrapositive says that if Y is not an L space, then lambda 1 star is small. So it's saying that non-L spaces are big. Okay, so a small eigenvalue implies somehow the space being big from the point of view of spectral geometry. Okay, so in some sense, I guess a lot of, I guess one of the big themes in fluid homology now is this relationship with being an L space and having non-left orderable fundamental group or non-having Todd foliations. And in some sense, you can think of those conditions as so being an L space. You should think of it as somehow a topological way of saying that your space is small in some sense. And I think this theorem puts this theorem that gives some kind of intuition behind that, at least from the point of view of spectral geometry. So it's some kind of quantitative sense in which non-L spaces are big in some sense. Okay, so this is how I think of this result. Okay. Yeah, so of course now the hard part now is like, of course, you have a nice numerical condition, and the problem is like, can we ever achieve other examples of manifolds for which this is true? And so to access this, so that's the natural question is like, are there examples with of hyperbolic rational homology spheres with lambda 1 star bigger than 2? Okay, so these manifolds turn out to be L spaces. Okay, and here is like, so far, I don't know if you remember, our original goal was to somehow relate hyperbolic geometry with flirt theory. Yeah, so far we related it with spectral geometry, and somehow it turns out that this very cool relationship between spectral geometry and hyperbolic geometry. So we can obtain information about lambda 1 star using the Selbert trace formula. Okay, let me just write it out for now, and then I'll comment on the significance. Yeah, so suppose, so now pick H, which is a C infinity with compact support function, even. Okay, some nice even test function, and H hat will be its Fourier transform. Okay, and then let's set, just for notation convenience, let's say Tj to be the square root of lambda j star. Okay, so the square root of the eigenvalue. Then we have the following relation. So here -1. So here I'm always assuming b1 equals 0, but yeah. But you can there's a formula for the holds in general. So the Fourier transform at 0 plus 1/2 the sum from j equals 0 at infinity of H hat of Tj. Okay, this will be volume of y divided by 2 pi times h of 0 minus the second derivative at 0 plus sum over all closed geodesics. Okay, of the length of gamma 0. So I'll explain all the terms when in a moment. Holonomy of gamma divided by 1 minus e to the complex length gamma times 1 minus e to the minus complex length gamma times the function h evaluated at the length of gamma. Okay, so this is a long formula. But yeah, so let me just mention what this is. So this is so here I'm summing over all closed geodesics, and any closed geodesic will be some multiple of for some primitive geodesic. Okay, so here this is the length of that primitive geodesic. That's you're the multiple of. Okay, and here we have the holonomy of the geodesic, and here this complex length. Okay, so the complex length, if you remember, was complex length. Complex length was the real length plus I holonomy of gamma, and this was in r plus I r over 2 pi z, right? So yeah, so we're taking e of it, the exponential of it, so we don't have to worry about well defined or not. So we have the cosine and then the function evaluated at L. Okay, so yeah, yeah. So why is this helpful? Well, I guess it's nice because so on one side of the equality, here you have the spectral side. Okay, so on the right, sorry, on the left of the formula, everything, the sum only depends on this eigenvalues of the Laplacian, which like T1 is the number we want to understand a little bit. Okay, while on the left, here we have the geometric side. Okay, so everything here on the right only depends purely on the geometry, hyperbolic geometry of the manifold. So in particular, you see, once you know the volume and the length of the geodesics, for any function, you can compute the right side. And using that relation, you can hope to get some information about the left side. So, can use, so the upshot is that can use computations in hyperbolic geometry to access lambda 1 star. Okay, so I guess this is the main idea, and in principle, yeah, what you do is like you do some kind of course, we can only do some finite computation, and then using this finite computation of geodesics, you can try to find good test functions H for which you can extract information about your spectral side. Okay, so this so here we follow like the so following Bucher and Strombergson. So they were facing, they applied the same technique in some kind of two-dimensional setting when studying like congruence covers of the modular surface. But yeah, so I guess so you can use computations on the right side. So given volume plus complex length spectrum up to some cutoff big R. So big R will be some, you look at all the geodesic for which the length is at most R. So R in our examples would be maybe 6.5 or something. Okay. Yeah, so from here, you can run some procedure to find good test functions. And using this, you can produce some function JRT. Okay, this is a function from 0 infinity to 0 infinity, which has the property that the key property of this function is that JRT is bigger or equal than the multiplicity of T star as an eigenvalue, T square as an eigenvalue. Okay, so the basic idea is that, so let's say this is the T coordinate, and we would like our hope would be to find the spectrum. So the spectrum, maybe you have eigenvalue here with multiplicity 2, and you have eigenvalue here with multiplicity 1. So this will be the kind of, so red, this is the spectrum. Okay, of course, given a finite amount of data, you won't be able to recover the spectrum exactly, but we will be able to write some code that spits out some kind of function that approximates this from above. Okay, yeah, so this will be our JRT. Okay, so in particular, we know that, so here, so in particular, this allows you to give lower bounds on the spectrum. So for example, we know that in particular, if JRT is less than 1, then T square is not an eigenvalue. Okay, so for example, in this toy picture, the stuff, we know that anything below here cannot be an eigenvalue. Okay, yeah, and this is something that you can run in practice. This is just because, yeah, so can compute geometric data using SnapPy. Okay, so SnapPy, if you ask for a manifold, it returns you the volume and the complex length spectrum up to a certain cutoff that you ask for. Yeah, so let me just tell you, this is what happens this is the picture that you get for weeks. Okay, so this is weeks. And I think for here, R is 6.5. Okay, so this took about 20 minutes of computation with SnapPy to compute the length spectrum up to that cutoff. Okay, so you can see that, yeah, so we know that this tells me that, yeah, so for example, well, you know, here is about square root of 2, somewhere there. So in particular, you know that the function, the blue function, is below 1 up to square root of 2. So you get that, so T1 is bigger than square root of 2, so you get that lambda 1 star is bigger than 2, so you get that Weeks manifold is a null space. Okay, so this is a proof using hyperbolic geometry. So all the input we got here was hyperbolic geometry, so the length of geodetics and the volume. And this is a proof that Weeks is a null space this way. Of course, you can prove that Weeks is a null space in many other ways. For example, it's a branch double cover of a quasi-alternating knot. Yeah, so I guess another thing is that so maybe I'll just say here. So, you know, so this is a finite computation, and the expectation is that if you let R go to infinity and run this thing should somehow converge at the delta, at the, should go, this blue, this black curve should converge for R very big to the indicator function of the spectrum with multiplicity. Okay, so I guess at least that's the expectation. So in particular here, the suggestion, you know, you have this curve, which is very nice and goes just slightly above 3 here. So you should expect, so they expect an eigenvalue, the real actual eigenvalue of the real first eigenvalue should be is around here, so about 9 with multiplicity 3. Okay, that's the real expectation of that. Okay, so for our method, really, we only want the function to be less than 1. But yeah, this kind of picture we built give you information also about some more refined information about the spectrum. Okay, any question? Yeah, so let me tell you about then the practical limit.
Francesco,
Oh, yeah.
sorry, I'll have a question. So back in this picture, I mean, it looks like you'd have an eigen value of multiplicity 3, but it's not guaranteed, right?
No, yeah, this is not a proof. Yeah, so it's a suggestion that there should be an eigenvalue there. So it's a proof that there's no eigenvalue less than 2.
Yeah.
But it's not a proof that there is an eigenvalue with multiplicity 3 there. Okay. Yeah.
Thank you.
Yeah, that's a good point. Yeah, so that's just so that's why I say we expect. Yeah. So, yeah, so let me tell you about some limitation of our method. So limitation. Okay, so first of all, yeah, so there's a lot of geodesic, first of all. So I guess there's a version of the prime number theorem that works. That it's the equivalent. There's an equivalent of the prime number theorem for prime geodesics in a hyperbolic 3 manifold, and that tells you that the number of primitive geodesics with length less or equal than gamma than R, this is about it grows exponentially fast. Okay, yeah, so in particular, so here we use some parameter R equals 6.5 that took us 20 minutes. Yeah, really, well, of course, the number of geodesic grows exponentially, so you can expect to compute stuff in less than exponential time. But at the practical level, the computation takes super exponential time. So computational time is super exponential in R. Okay, so, and in particular, well, so as far as you look at this small manifold, it's not that big problem. But yeah, I guess when volume gets large, I guess naively, just because of the Weil law tells you that the number of eigenvalue depends on the volume. So the bigger the volume is, the more eigenvalues you expect. You expect more eigenvalues. So when you have more eigenvalues, it gets harder and harder to get this nice like curve bumpy around each eigenvalues, right? So you can expect if you have a bunch of eigenvalues which are pretty close, then you won't be able to see them very well unless you look, you will like something that goes like this. But to do that, you will need to compute a lot of geodesics, and that takes a lot of time. Okay, so having a big volume, it's a problem from our perspective because you need to compute many more closed geodesics, and that it's super exponential in time. Okay, so so let me just tell you what happens when you do Seifert Weber. So Seifert Weber. Okay, so well, let me just show you the picture we get. Sorry, let me just go here. Yeah, so this is the picture of Seifert Weber. Yeah, so you see that so Seifert Weber. Okay, this is the cutoff is R equals 8. And this, it wasn't too bad. So this only took 5 hours to compute. So I think Seifert Weber is somehow special because, well, the fundamental domain, it's this thing behind me. It's super nice. It's very symmetric and stuff. And in fact, the computation before that the computation that for weeks took 20 minutes, for Seifert Weber only takes 12 seconds or something. So it's something super fast. So a computation already at R equals 8 for weeks, I don't think it's something that's it's in a reasonable amount of time to compute. But yeah, so if you just look, so if you look where JRT is less than 1, you only get that lambda 1 star is bigger or equal than 1.91. Okay, which is close enough to 2, but it's not enough for us to prove that Seifert Weber is an L space. The Seifert Weber space is an L space. Okay, so this is extremely fast. Okay, so of course then, but if you look at the picture, well, there's this nice peak around, there's this nice peak right above 6, right? That's the picture suggests that, and here I as Rafael was suggesting, I was mentioning, this is only a suggestion, it's not a proof, that the first eigenvalue should be about, if you do the computation, it should be about 2.03. Something, and multiplicity 6. Okay, so I guess the idea, of course, you know, we expect this, if you compute even more and more length spectrum, well, this kind of peak should get smaller and smaller. So the hope is that if you compute enough, at some point this curve will cross 1 above square root of 2. But if you run just a heuristic computation, you should need at least, if you're optimistic, R equals 9.5 will work. And that, being very optimistic, will take at least 3 or 4 months with computation on SnapPy. If you expect things to just grow exponentially, which things don't really. So yeah, so you know, there's kind of this computational barrier between us, and you know, from the picture, it's clear that at this point, if you just look at the picture, it's clear that Seifert Weber is an L space. But yeah, this picture doesn't give you a proof because we cannot really prove that lambda 1 star is bigger than 2. Okay, so yeah, so when we saw this picture, of course, we say, oh yeah, of course, Seifert Weber will be an L space. But then you have to figure out, yeah, one way to get around these computational problems, right? And yeah, so I think, so far, we didn't really use anything particularly important about Seifert Weber. But yeah, so I think the idea is to somehow show that the eigenspace has big multiplicity. And that would be our goal now. So the claim. So on Seifert Weber, the multiplicity of any eigenvalue which is less or equal than 64. Okay, it's a weird number, but just we really need less than 2 or something. Has to be at least 4. Okay. Yeah. So now, so really now we are not interested anymore in where this function crosses 1, but where this function crosses 4. Okay, so yeah, so then, well, from this picture, it's pretty hard to see, but if you zoom in, you get this picture. So this is, again, JRT for R equals 8. Okay, and square root of 2 is somewhere, it's 1.4 something, right? So it's here. So this is square root of 2. And in this thing, it's slightly more. So this is about 1.4143 something. So in particular, you can show, just because we should prove that the eigenvalue has to be bigger than 4. So your real eigenvalue would be about after this intersection point. So you get that lambda 1 star actually is bigger than, let me see, 0.04, which is bigger than 2. Okay, so, and this will prove that Seifert Weber is an L space. Okay, so yeah, so we have to go through, well, of course, you can get, if you don't feel safe with these digits, you can go a little more, do computation up to 8.6, and then you get maybe one less 0 or something. But yeah, so I guess the main idea of our approach to prove that Seifert Weber is a space is that, yeah, so our previous work only used that multiplicity 1. But here, somehow, we can use extra properties of Seifert Weber, the Seifert Weber space, to prove that eigenspaces must have some kind of big multiplicity. So we can exploit these big peaks in the graph in this function we built. Okay, any question?
Francesco, sorry, you may have said that before, but how did you construct that? How did you get that function JRT again? Was that from?
Oh, so yeah, so I didn't really explain it, but yeah, in some sense, from the trace formula, we know everything on the right side.
Yes.
And then you just pick some nice function that gives you bound on eigenvalues on the left side.
Okay.
So in some sense, yeah, you use all the information here to build some kind of bounds on eigenvalues, yeah.
But do you build the functions h cleverly or the functions h hat?
Yeah. So I guess yeah, h has to be chosen. Yeah, so it's not chosen, like it's somehow there's the code that finds the right h in each situation. Yeah. So so h would be some kind of the way the code works is like you find somehow the best h in some finite space of test function that work. Yeah, so the code is like looking for the best function given the data you input. Yeah.
Okay.
Yeah, there's some kind of optimization problem involved in building this JRT. Yeah, so unfortunately, I don't have much time to go through how you build it. Okay. So it's kind of a black box that you give the length and this spits out this function. Yeah. But yeah, so yeah, that's a good question. So yeah, the problem of this is that I don't really know. You know, it would be cool to say, oh, if a space has a geodesic with this length, then it's an L space. But yeah, the way our code works, it's really unclear if you can make any statement like that. But that would be very cool. Yeah. So okay, now all I want to
Francesco, do you expect all the eigenvalues to have a multiplicity at least 4?
I think I don't know about the yeah, I don't think the big ones we can say much. Yeah, we cannot say much about the ones. Yeah, I don't think we can say that all the eigenvalues have multiplicities 4. Yeah. Because there might be some, I guess from the proof, yeah, the eigenvalues of the quotient will be, those might not might have just a trivial representation upstairs. I guess that will be the problem. But yeah, maybe let me go through the proof and then we can, yeah, maybe from there. Yeah, that's a good question. It could be possible though. Yeah, there's no reason why it shouldn't be. Yeah, I don't know. But yeah, of course, our proof doesn't show that, I think. Yeah, so this will be putting together 2 facts. Okay, so fact 1. Okay, so Seifert Weber the Seifert Weber space has a very big isometry group. The isometry group, and that turns out to be all orientation preserving. This is isomorphic to the symmetric group. Okay, this is due to Nick in 87. Okay, so how do you see this? Let me just tell you how you see this group. Well, of course, we know this is like the dodecahedron has the isometry of the dodecahedron is the alternating group. So A5 is the isometry of the dodecahedron. Okay, the group of rotations that preserve the dodecahedron. Okay, so in particular, well, if you think about it, the way Seifert Weber is glued, you just pick two opposite faces and glue them, and this group, this phase pairing, is preserved by rigid transformation by rotations. So in particular, A5 acts as isometries on Seifert Weber. Yeah, and the quotient Seifert Weber mod A5 is an orbifold. So it's this orbifold here. So it's this orbifold. So it's the underlying singular locus is just the the one skeleton of the tetrahedron, and the orbifold locus has this kind of 2, 2, 2, 5, 5, and 3. Okay, so each edge you have an angle of 2 pi over the edge. Okay. Yeah, and the nice thing now is that this is, you should think of this as an orbifold in S3. So it's S3 with this orbifold singularity. And you see that, well, this orbifold has a very nice extra symmetry, right? Because you can do, if you look it from above, well, you have this rotational 180-degree symmetry around this. Okay, so if you just rotate it, it goes to itself. So this gives you an isometry of the quotient. And the cool thing is that this extra isometry actually gives you, is compatible with the isometries of Seifert Weber. So actually it gives you an isometry of the Seifert Weber space. Okay, so you get, I guess the non-trivial observation is that this induces an extra isometry of the Seifert Weber space. Okay, yeah, so what you get is that, yeah, in particular, well, you have this very big isometry group. So the symmetric group acts on each lambda star eigenspace. Okay, so each eigenspace comes, just because it's an action by isometry, you can pull back eigenforms, and there'll still be eigenforms. So you get each eigenspace will be very big. Yeah, so the fact that I want to, the second fact is that if lambda star is less or equal than 64, then the lambda star does not contain copies of the trivial A5 representation. Okay. Yeah, so from here you can conclude that the eigenspace each eigenspace has to be at least 4-dimensional, because you look at the representations of S5. So S5, so you look at the irreducible representation there. Well, the dimensions are 1, 1, 4, 4, 5, 5, and 6. And this is the trivial representation. And this is the sign representation. And they both restrict to the trivial representation of A5. Okay, the trivial representation, of course, and the sign representation is defined to be trivial on A5. Okay, trivial when restricted to A5. Okay, so this implies that when you look at this decomposition, this eigenspace, well, you can decompose it in irreducibles, and there won't be one-dimensional things. So the dimension has to be at least 4. Okay, so this is some nice observation from finite group representations that allows us to conclude. Okay, so yeah, so all it's left is to prove this fact too. So each eigenspace does not contain copies of the trivial A5 representation. Yeah, and how do you do that? Yeah, so I guess the observation is that, so if you have, so trivial A5 rep inside V lambda star, this corresponds to a lambda star eigenform on Seifert Weber mod A5. Okay, so an invariant, so trivial representation, a trivial A5 means that this eigenform is invariant under the action of the alternating group, so it descends to the quotient. So the idea is to show that, so I need to show lambda 1 star, the first eigenvalue of this Seifert Weber mod A5 is at least 64. Okay, because then that thing doesn't have eigenvalues. That every eigenvalue above, which is a trivial A5 representation, will give me an eigenvalue downstairs. Okay, yeah. So let me just mention quickly say how to do this to prove this. Yeah, so really the Seibert trace formula works for orbifolds too. So of course, now like doing Floer theory on an orbifold with this kind of singularity is probably the worst nightmare of any Floeromologist, right? Yeah, now it's nice because everything is a linear problem. So we are just looking at like finding eigenvalues is a linear problem. So we don't really, we're not really that worried about bad orbifold singularities. Yes. So in particular, there's a version of a Seibert trace formula for orbifolds. Okay, and yeah, the only extra complication is that, well, this kind of orbifold is too complicated for Snap. It's not implemented in SnapPy, so we cannot use SnapPy to compute its length spectrum. So but the nice thing is that this is to compute length spectrum. Well, the key point is that Seifert Weber mod A5 is a very nice, it's a very simple, very explicit arithmetic orbifold. Okay, so you can think of it, yeah, it's some kind of, it's a nice group of matrices. So you can think of it, I guess, very roughly speaking, you should think of it the analog of some kind of analog, some kind of PSL2Z. This is the modular surface, and you should think of it. This corresponds to the field Q, and Seifert Weber mod A5 corresponds to the field Q adjoint -1 -2 square root of 5. Okay, so this is the modular surface. Yeah, so it's very classical that lengths of geodesic on the modular surface correspond to like fundamental units in some kind of quadratic extensions of the rational numbers, and the multiplicity are some kind of class numbers. Yeah, so there's some kind of the analog holds for these more complicated objects related to this kind of more complicated field. And yeah, so this is described. So this is described by Voigt in his book on quaternion algebras. And it's implemented by Page in PariGP. So I guess number theories have these magical tools that allow you to compute all these things, all these lengths of geodesic in this very complicated orbifold. Okay, and it runs pretty fast. So you can do, you can run our code. You have to be careful because now it's an orbifold, so you have elliptic and other kind of elements. And I'll just conclude by showing the picture you get in the end. So this is the picture you get for Seifert Weber mod A5. And this is JRT for R equals 8. Okay, and you can see that there's no, it's less than 1 for t less than 8. So this implies that lambda 1 star of Seifert Weber mod A5 is at least 64. Okay, and then it tells me that, again, the multiplicity in Seifert Weber of all the eigenspaces is at least 4. And that's how we conclude the proof. And I guess I'll stop here. I'm slightly over time. I'm sorry.
Francesco, could I ask a question?
Yeah, sure.
So going back to just this Seifert Weber space in its definition, does its fundamental group have other interesting finite quotients apart from just the abelianization?
Sorry. About Seifert Weber?
Yeah.
So Seifert Weber, yeah, I'm not sure about that. Yeah, that's a good question. Yeah, I don't really know about other interesting quotients of the fundamental group of the Seifert Weber space. Yeah.
Okay. Thank you.
Yeah, sorry.
No, it's okay.
Yeah, so then he asked, does this mean that, yeah, so if someone tries to embark and define Floer homology for orbifolds, this should say that Seifert Weber model 5 is an orbifold space. I guess that's a natural theorem that once defines the object, that should be true. Yeah. And Ali asks, is the hyperbolic metric ideal? Yeah, that's not clear, but yeah, so that's a good question. Like, in principle, no, but that's the hyperbolic metric is the only metric for which you can do some kind of explicit computation, because we really need very explicit numbers, right? And that's the only way you get them is for the hyperbolic metric. If maybe there's a better metric, but we cannot do any kind of computation for this other metric, that even if it's better, in principle. Yeah, so regarding Ian's question, I think, yeah, these eigenvalues, yeah, so there will be 2 eigenvalues here in the quotient, and yeah, I'm not sure if when you pull them back, they will stay multiplicity 2, or they might get higher multiplicities. That's, yeah, you might have just these eigenvalues with multiplicity 2 when you pull back. Yeah, that's not clear. Yeah.
Francesco, there are a few questions in the chat that you may have overlooked.
Oh, really? Okay, sorry. Yeah. Oh, yeah. Oh, yeah. So Raphael asked if there are SU2 representations. Yeah. So the nice thing about yeah, so it's not SU2 cyclic, and that just follows from the number theoretic definition. So if you look at this definition, this really you realize it's a subgroup of PSL 2C. Okay, but and this you can that's the geometric group of hyperbolic space, and that corresponds to the embedding of this field inside C. But this field also has some embeddings inside R, and if you just take the Galois conjugate of this embedding, you go inside SU. So if you take Galois conjugate, you will get a representation of this orbifold A5 into SO3, and that leads to a representation into SU2, which is irreducible.
I had just tried it with gap actually, so you know you can make it.
Okay,
work.
so
Yeah.
it's right?
Yeah. I mean, there are definitely some A5 representations.
Oh,
which
yeah,
is-
yeah, okay. Mhm.
But my question
Oh.
was that what are all the representations? Do you know the whole SU2 character variety?
Oh, well, no, I don't. Yeah, maybe someone, maybe in the audience does. Yeah, yeah, I don't know the other representation. Yeah, yeah, actually, yeah. So this orbifold has, yeah. Sorry, maybe, yeah. Sorry, if you take the Galois conjugate. Yeah, and Ian asks, yeah, the other branch cover of the weighted link. Yeah, that turns out, yeah, it turns out that if you have that's a branch double cover over a link in S3. And I think it's in Nathan's census of branch covers. It's the branch double cover over a link with 15 crossings or something. Yeah, in general, it's a fact that if you pick a two-bridge knot and look at the cyclic cover that sends both meridians to 1, then that would be the branch cover over a link in S3. So those are somehow simpler to understand from this perspective. Yeah. Yeah, that's everything. Seifert Weber Carré-Todt foliation. I guess the main theorem it's an L space, and L spaces don't admit Todt foliation. So yeah, I guess this is a corollary of the main theorem that this space doesn't have a Todt foliation. Coorientable, at least. Okay.
I'm just going to repeat Tom's question. Is the fundamental group of stably left?
Oh, sorry. Yeah, sorry. I missed that. Yeah. Yeah, I don't know. That's a good question. Yeah. Well, I guess I guess if the conjecture is true, it shouldn't be. I always get confused. Yeah. So it shouldn't be left orderable. Yeah. So. Yeah, I'm not sure. I don't know if it's known. Okay, this technique can only work for finitely many manifolds. Yeah, I guess that's a good question. So I guess a very hard question is like, first of all, are there infinitely many hyperbolic 3 manifolds for which this is true? And that's, so far we don't know. Like, it seems a very hard question to find infinitely many examples. And among those, like, yeah, it might be that using these multiplicities, you can hope to, using this multiplicity approach, you can try to hope to find more examples. I guess the problem is that, yeah, multiplicities, yeah, if you look at like PSL to FP that has order P cubed, so if you look at manifold with that action, the volume will be about P cubed times, at least that times a constant, but the representation, the multiplicity will only grow linearly. So I think for those in general, I guess the natural place to look for these are congruence covers, which have these isometries PSL to FP. And yeah, and those, like, yeah, it's unclear if there are infinitely many cases, but it seems at least that there shouldn't be. Yeah, it seems like kind of a very special example in which all these coincidences happen that we can actually do the computation. Yeah, so I'm not sure if there are other manifolds for which we can apply this technique. Can you get Seifert Weber by surgery on the Poincare sphere? Like by, yeah, okay. Sorry. Yeah, so yeah, I guess trivia is that, yeah, at the beginning, we had this thing, and if you do 3/10 of the turn, you get Seifert Weber. If you do 1/10 of the turn, is the Poincare homology sphere. But yeah, it's not that clear how they're related. Yeah, and I guess Ian also asked, lambda 1 star will be less than 2 for either small injectivity radius or large volume. Yeah, so I don't think. So yeah, small injectivity radius, it's true that lambda 1 star will be small. In principle, large volume doesn't have a correlation, as far as we know, with lambda 1 star being small. So yeah, in principle, one could hope to find infinitely many examples, but our computational tool at the moment really works for specific. If you give me a specific manifold, we can do the computation. And yeah, it seems hard to generalize this technique to infinite many examples. I guess, yeah, the analog with lambda 1 uses techniques from analytic number theory and stuff, but that seemed not to work very well for lambda 1 star. So yeah, that seems like the extra complication of this is that, yeah, number theory doesn't help that much for this problem.
Is the orbifold where you take the quotient of Seifert Weber by the Z5 action, is that amenable to SNAPy?
Yeah, if you do this, if you do the Z5 action, you get the S3 with the weighted link.
Is that amenable to SNAPy to compute?
Oh yeah, yeah. SNAPy does the computation for this, but the
Uh-huh.
representation theory of Z5 is not interesting enough for us to conclude.
Uh-huh.
Because
But
it
it
only,
is still-
you can only tell that you have to pass 2 or something. Yeah, but yeah, that somehow, I guess the smallest irreducible, I guess we tried that, and for some reason we
doesn't
couldn't
work. Yeah, okay.
couldn't conclude. Yeah, so we needed the full quotient. And yeah, I guess the coincidence is nice that this thing is a very, well, from our perspective, is a very nasty object, but for number theorists, is a very nice object. So it's like bread and butter for number theorists, this orbifold here. So
Is there a twisted version of Selberg trace?
Twister?
Twisted. I mean, so if you take a representation of the fundamental group.
Yeah. I think yeah. There should be there should be a twisted version too. Yeah. Mm-hmm. Yeah, I think you can get the version for more or less any natural differential operator on your space, which is somehow a quotient of a quotient on a differential operator on H3 by some group action with maybe a twisting. Yeah.
One more question. Yeah, so it looks like that that eigenvalue, lowest eigenvalue, is actually multiplicity 6 from your computation.
Yeah. So yeah, it should be this. It should be this representation, like the exterior lambda 2 of the standard representation.
Mm-hmm. So
S5 has this 6-dimensional representation, but yeah, we don't know how to prove that it's actually 6-dimensional. Yeah. So. Yeah, so I guess maybe we can look at other quotients and some rep theory of S5. One could try to show that it's 6-dimensional. But yeah, of course, that's a natural. The natural conjecture is that eigenvalue is 6-dimensional. The eigenspace 6-dimensional with eigenvalue 2.03. Yeah. So Chatai asks, any room for improvement to your result from 2018? I guess this is about the estimate. Oh, sorry, it was a private question. So yeah. So I thought about it quite a lot, but no, I don't know how to improve it. So it seems, integration by part is very nice. If you try to go through other techniques, you get just stuff up to constant. At least the techniques I tried only get estimates up to other constants, and those are not very useful in this kind of problems where you really need actual numbers. So somehow, yeah, this is these estimates from 2018 so far. I'm not sure what would be a way to improve it, but of course that would be a very cool way to try to incorporate other geometric quantities, well, like volume injectivity radius to start with. Yes, for example, at the moment it's unclear whether if you do large surgery on a null space knot, then there will be solution to Seifert-Witten equations or not. So if you can prove something like that, that would be very cool using these tools. But yeah, I don't. Unfortunately, when the injectivity radius goes to 0, lambda 1 star also goes to 0 on a rational homologous sphere. So there's no this thing that this criterion doesn't apply there.
Francesco, I have a question.
Yeah.
So it looks like, okay, so you are using this Bochner technique to give some, to rule out the existence of irreducible solutions. But it looks like, okay, so if you just do this version, it works, basically, it doesn't really distinguish between torsion spin C structures, right? The estimate are all the same for each.
Yeah. That's yeah.
And well, somehow related to Tom's question, is there some kind of twisted version that can give you different estimate for different torsion spin C structure on your rational homologous spheres?
Yeah, that's a good question. That would be very cool, I think. Yeah, I'm not sure, but yeah, that's an interesting point because yeah, sometimes like when you look, for example, a lot of spaces have Floer homology just rank 1, so you would expect some stronger estimate for all spin C structures except 1. But yeah, I don't know. I didn't come up with anything related to this. Yeah. Yeah. But that's definitely a good observation. That some twisted version of this might help you showing that certain species structures have yeah.
6.
Okay, thank you, Francesco. It seems like we had a lot of questions and a lot of engagement today.
Oh yeah, it's fun. Yeah.
Nice talk.
Thank you. Hope everyone is doing fine.
Yeah, okay. Thanks again.
Thanks.
Great talk, Francesco. See you later.
Thanks. Did your son like it?
Oh yeah, I think you like it, honey?
Yes.
Okay.
All right. I'll talk to you later.
Okay, see you.
Bye.
Francesco, this is Ian. There was, I think that Nathan found some other example in the snappy census that was an L space and satisfied the arithmetic criterion that we needed for our theorem. Did you try this technique on that example? Do you remember what I'm talking about?
Bye. Thank you.
The meeting's going to time out now. Thanks, everybody.